This lesson is 8.5, Write and Graph Exponential Growth Functions. You should be on page 520. An exponential growth function is a function of the form y equals a times b to the x power, where a is a number other than 0 and b is greater than 0. b also can't be 1. Okay, so I guess another way to put it is a can't be 0. Maybe I should just write it over here. A, what I'm pointing to here, a cannot be 0 for this to be an exponential function. And b has to really be a number, it's got to be more than 0 but not 1. Okay? Exponential functions are nonlinear. So think about that word. Now, I think you know what linear means. Linear means straight line. So what would nonlinear mean? And I hope you're coming up with, well, that means it's not straight. Okay? Exponential functions, when you graph them, are not straight. They're curved. So this is telling us we'd have a curved graph. Okay? Observe how an exponential function compares with a linear function. Let's review a linear function, y equals 3x plus 2. They made a little table in their calculator of this, and I want you to notice on the table, as x goes up 1 each time, y would go up 3. Do you notice how there's a constant addition pattern in a linear function? And you might be like, well, why do we have that constant pattern? Well, think about it. The slope is 3. Rise 3, run 1. Rise 3, run 1. A constant pattern. An exponential function has a different pattern. If you go ahead and you put this in your graphing calculator, y equals 2 times 3 to the x power, you would get this table right here. Let's examine this table. Now look at how it's different. We're not increasing 3 each time like we did here. We're not adding 3. We're timesing by 3 to get from one to the next for every one we add. So I guess the big difference between a linear and exponential function is that a linear function, you can see in the table, has an addition or subtraction pattern. This is an addition pattern, where an exponential function has a multiplication pattern. That's the big difference between the two. Let's talk about writing a rule for an exponential function. So the first thing we need to determine is the function even exponential. And if you look at this table carefully, can you see how 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and we keep on increasing by 1 for x. I see a multiplication pattern. So let me highlight that here. I have a multiplication pattern. This has to be an exponential function. Now, exponential functions always have the form, let me highlight it in green, always have the form y equals a times b to the x power, which I'm going to just draw here. I wrote it up here again. Now, a and b have a special meaning in an exponential function. A is the y-intercept. It's where your graph crosses the y-axis. Now, if you look at this table carefully, do you see the point 0, 8? Mentally picture that point in your head. Isn't that 8 units up on the y-axis? The a value for this table has to be 8 because that's the y-intercept. Now the letter B stands for the number that is multiplied each time. I should probably not of, but that is multiplied each time. Okay? Do you notice how on this table we're multiplying each time by 2? That means B is 2. So B has to be 2 because we're multiplying by 2 each time. So my equation, you can see, y equals a times 2 to the x power. Let's write a rule for this function. Now notice, first of all, I'm increasing by 1 each time for x. for y, can you see a pattern of times 3? So this is a definite exponential pattern, and I would use y equals a times b to the x power. My y-intercept is right here, it's 27, so a has to be 27. And since I'm multiplying by 3 each time, b is 3, that would be the equation for that table. Now, you might want to pause the video, type that equation in your calculator, make a table, and just double check, is it what you have here? And it will be. Graphing an exponential function. When you graph an exponential function, here's the first thing I need you to know. You will always get a curved graph. It will always start low, pass the y-axis, and explode upward. I guess that's kind of where exponential kind of sounds like explode. Okay? Exponential functions will start low in the negatives for x, and then it will pass the y-axis and explode up. All right? To graph this function, you can use your calculator. Y equals 2 to the x power. You'd make a table and plot the points, and you can see that's happening here. Start low when x is negative, pass the y-axis, and then explode upwards. Now the domain and range. The domain, what x values can I use? Well, x could be negatives, x could be 0, x could be positive. So my domain in this problem would be all real numbers. I can use anything for x. Now let's look at the range. The range is the y's. Look at this picture. Y's are always positive. They get closer and closer to 0, but they never touch 0. So my range would be y greater than 0. My y values have to be 0 for this. When you do the homework, this is similar to something you did earlier in the year with linear functions. They will have you graph a function and then compare the graph with the graph of the parent function. Now when you compare, you're going to write two sentences. You're going to write how the y-intercepts compare, and you will also compare how the graphs are related by whether they're stretched, shrunk, or reflected. So for example, here you can see the graph of y equals 2 to the x power, I'm going to highlight it in green, would be this right here. You can see it's the graph starting low and exploding upward. Now how does y equals 3 times 2 to the x power compare? Well, I'll graph this one in blue. You notice the values are 3 times greater. So this graph would be stretched by a magnitude of 3. And when I compare the y-intercept, this graph has a y-intercept of 3, while the parent function has a y-intercept of 1. If I compare this graph to the parent function, the negative value in front is going to multiply all the values by negative 3, which is going to reflect my graph. This is the one that's opening downward, and it's taking all these values and multiplying them by 3. Okay? So when they ask you to compare, you'll graph the function, you'll graph the parent function, and you'll write two sentences. How do the y-intercepts compare, and how does the function compare to the parent function regarding stretch, shrink, reflect? Let's try one of those. I'm going to graph y equals 1/3 times 2 to the x power and compare it with the parent function y equals 2 to the x power. So y equals 1/3 times 2 to the x power and y equals 2 to the x power. Let me do the parent function first. The parent function, here's the table for it. I could plug this in my calculator. Here's my table. Let me plot those points. So -2 1/4 and -1 1/2 and 0, 1, 1 right, 2 up, 2 right, 4 up, and so on. I'm then going to take my pen and as best I can draw my curve. And you can see this starts low, passes the y-axis, and explodes up. Now, how does this graph compare to this? Well, do you notice how this has a 1/3 in front? Here's what that 1/3 is going to do. It's going to take all these y values that I'm highlighting in blue. Let me highlight those in blue. And it's going to multiply all these values by a third. Okay? So when I multiply these values by a third, here's what I'm going to get. 1/4 times a third is a 12. That's supposed to be positive. I got to change it to positive 12. Okay? A third of a half's a 6. 1 times a third's a third. 2 times a third's 2/3. 4 times a third is 4/3, and 8 times a third's 8/3. So this graph, can you see how it's 1/3 the size? It's 1/3 of the way lower than the parent function. Now I got to write two sentences comparing the two. Let's compare the y-intercepts first. The y-intercept of 1/3 2 to the x power is the ordered pair 0, 1/3, while the y-intercept of the parent function, you can see here, is 0, 1. Let's compare how they stretch and shrink, whatever now. This function, y equals 1/3 times 2 to the x power, is shrunk by a magnitude of a third when compared to the parent function. In other words, all these values for y on this function are 1/3 of the size of the values for y in the parent function. That's what you need to do on your homework when they ask you to compare a function to the parent function. Graph them both and then write two sentences. One comparing how they intercepts compare, the other how do they shrink, stretch, or reflect. Exponential growth is when there's a model for that right here. When a is greater than 0 and b is greater than 1, the function y equals a times b to the x power, exponential growth, would represent growth. That means that the values will keep increasing. When a quantity grows exponentially, it increases by the same percent over equal time periods. To find the amount to which the quantity grows after t time periods, use this model. So I would pause the video and get this model in your notes. This model is telling you the following, and I should write in one other thing here. Y represents the total amount. Okay? A represents the initial amount you have. R is the growth rate. I should put down, we want to write this as a decimal. And T is the time periods. We can use this model in money problems, okay? Meaning figuring out, calculating money. The next page, we see the term compound interest. Compound interest is interest earned on both an initial investment and on previously earned interest. Compounding of interest can be modeled by the exponential growth model, where A is the initial investment, R is the annual rate, and T is the number of years money is invested. So I always like thinking money on this, one, because I know you're interested in money, and two, here's something we can use to plan for the future. We've had a couple projects now, one on the cost of living, a second on the cost of college. Some of you have figured out we need to start preparing. This model can help you prepare for future spending, all right? So to finish off the video, you're going to need your calculator. We're going to use the exponential growth model, which you see here, and we're going to use this to do this problem to give you an idea of why this model is kind of interesting when we talk about money. Suppose on the day you were born, your grandparents gave you a gift, $1,000. However, there was a catch. You could not have that money until you were 10 years old. They then took the money and they put it in a place that got 10% annual interest on that $1,000. Let's use this model, the exponential growth model, to determine how much you would have when you're 10 years old. So first of all, we got to fill this in. The initial amount is $1,000. That's A. 1 plus my growth percentage. We have a 10% interest rate. Now as a decimal, 10% is 0.10. And I'm doing this for 10 years. This would be 10 time periods. So what I need to plug in my calculator is 1,000 times 1.1 to the 10th power. So let's do that. So you can see here, I've taken my calculator, I've typed in 1,000 times 1.1 raised to the 10th power, and that tells me that at age 10, the $1,000 that my grandparents gave me because I got 10% interest every year would be worth, I'm going to round this to the dollar, $2,594. So let me write that down. At 10 years old, I had about I said it was $594. $594, okay? Hey, that's not bad. Now think about that. Your grandparents gave you $1,000, you didn't do any work at all, and you made an extra $1,594 over time because you waited till age 10. Let's figure out how much you would have if you waited until age 20 to get your money. So for that, you'd take 1,000 times 1.1, because it's 1 plus the 10%. This time we're going to do 20th power. Let's type that in our calculator. You can see that I've done that here. So at 20 years, it looks to me like if we waited till we're 20 years old, our grandparents' gift of $1,000 would be about $6,727. Let me write that down, $6,727. So if I waited till age 20, I just made an extra, well, I'm rounding in my head, an extra, what, at least $4,000, an extra $4,000. I didn't have to work for it, okay? What I would like you to do after you pause the video is I would like you to figure out the next four. How much would you have if you waited till you're 30 years old? How much would you have at 40? How much would you have waiting until 50 and then until 60? I will ask these on my audit. So definitely calculate those, and you can round them to the whole dollar. I'm going to pause the video here. If you have questions, you can ask in class.